Clutter filtering in color flow imaging is a challenging task due to the limited number of samples available in a packet, and also due to the fact that the clutter is not stationary. So the clutter filters that are used in color flow imaging have some certain transition region which can cause signal dropouts or biased mean velocity estimations. In this work, we wanted to investigate how we can use adaptive spectral estimation methods to avoid clutter filtering prior to mean velocity estimation. And by utilizing the low side lobe levels of adaptive spectral estimation method. Here you see two cases. The top spectra are generated using an adaptive spectral estimation method, and the bottom ones are generated using FFT approach. And here you can see that the clutter is confined in a small region in adaptive spectral estimation spectra. And the packet sizes here are 12 for this case and 10 for the in vivo case. One of the methods we looked into was CAPEN. It's the Filterback Approach. So it creates a filter for each frequency in the spectrum. And the filter is designed to minimize the output power while passing the frequency of interest undistorted. Another method we looked into is blood iterative adaptive approach. It's a similar approach to CAPEN. The difference is that the covariance matrix is formed with some initialization numbers, and the amplitude in for each frequency is estimated iteratively using the covariance matrix and the amplitude. And when the amplitude is converged to a certain value, the algorithm is terminated. So I'm going to go through the steps in our approach. First, we estimate the spectrum with the adaptive spectral estimation method. Later, we remove the threshold. We remove the clutter by setting a threshold in the frequency domain. So it's basically setting the frequencies under some threshold to 0. And later we calculate the mean velocity in the frequency domain using the autocorrelation method. And finally we compared the results from this method to conventional autocorrelation method, and using a suitable polynomial regression filter for autocorrelation method. And what I mean by suitable filter is that the filter with minimum order that can remove the clutter. And we did simulations for different SNR and packet sizes, and also flow phantom experiment and in vivo acquisition. And here is the simulation setup. We used packet size 8, 16, and 32, and for each packet size we used 5 and 20 dB blood SNR. Clutter SNR is fixed to 40 dB, and the bandwidth of the blood signal is changing with or increasing with velocity to mimic the transit time effect. Here is the result for 8 packet size and 5 dB. The filter order we used for regression filter is 2. And the black curve here shows the frequency response of the filter. And red curve is showing the autocorrelation method results. Here you see the bias and the standard deviation for different velocities. The blue curve is showing the results for CAPEN method, and this dashed line is showing the threshold we used for the adaptive spectral estimation method. Here you can see the difference in low velocities where the filter has its transition region, the autocorrelation method has a higher bias than the Capon approach, and there is not a big difference in the standard deviation. And the green curve is showing the BIA method. As you can see, it has higher standard deviation for these settings, and also higher bias. And when we increase the SNR to 20 dB, keeping all the settings the same, we see that BIA has a lower standard deviation, but still has the highest bias. And even though the bias is a bit smaller between Capon and autocorrelation method, there is still a difference for the low velocity. When we increase the packet size to 16 and the filter order to 3, we see that the region where there is difference between the adaptive spectral estimation methods and the autocorrelation method is decreasing, but still there is a difference in bias for low velocities. And still for this low SNR, BIA has a higher variance standard deviation than the two other methods. When we increase the SNR to 20 dB, there is not a big difference in standard deviation or in the bias for all the cases. And here also you can see that with increasing the packet size, we can also set the threshold for adaptive spectral estimation methods to a lower frequency, because the resolution of the spectral estimation methods are increasing. And you can see, even though this is a low SNR, all the methods are performing similarly. And for the 20 dB case, there is not a big difference between all these three methods. We also did some flow phantom and in vivo acquisition. Here is the acquisition setup, and we calculated the flow profiles along these lines and along the common carotid of healthy volunteer, and also the tube, which is the flow phantom. It has 6 millimeters diameter, and here is the result for flow phantom experiment. Here you can see in the middle of the tube there is not a big difference where the high velocities are present, but when we go towards the tube wall, we can see that the difference in bias is increasing. And we also have a reference here, which is 32 packet size autocorrelation method, and this black curve. And as you can see, Capon is giving values that are closer to this reference autocorrelation result. And for example, here, point close to the tube wall, the difference in bias between the Capon and autocorrelation method is 4.3 centimeters per second. And the filter size we used, filter order is 1, and the packet size we used for this setting is 8. And here is also the in vivo result. Here you can see that autocorrelation method has bias, or positive bias for all the velocities in the common carotid artery. And we used 86 lines along the tube and to calculate the flow profiles, and 110 lines for the common carotid. And here is one color flow image. This is a flow phantom result. Here you see the flow profiles, and you can see that the Capon approach can visualize the low blood velocities it has a smoother blood flow profile, while autocorrelation approach is giving, or the signal dropout close to the 2 volts for autocorrelation method. So in summary, the adaptive spectral estimation method can visualize the low blood velocities that would be attenuated by the filters in autocorrelation method. BIA has higher variance and bias for low velocities and also for low packet sizes. So the methods can potentially give better color flow images, but at increased computational cost, and BIA being the most expensive. And also another disadvantage with adaptive spectral estimation methods is that they need a certain spatial averaging region to give robust estimates. And here is one color flow clip, and you can see that along close to the 2 volts, we can visualize the